We're asked to find the graph of the following function in two-dimensional space, and we'll notice that the two variables that are present here are the z variable and the x variable. So when we graph this in two dimensions, the output or the dependent variable is z and the independent variable is x. So we're going to label the horizontal axis, the independent axis, with the x variable. And in this case, our dependent variable is z, so the vertical axis is going to be the z-axis. So we're actually graphing this in the xz plane. And we essentially treat the z variable just as we would if it were a y variable. So in order to use transformations and graph this in two-dimensional space, we need to factor out that negative on the inside here. So we'll get x minus 3 like this. And now we can treat it as a shift to the right, but also a horizontal reflection. So this negative here is going to be a horizontal reflection, and then we're also going to shift this thing to the right 3 units. And of course, we had to factor that negative out to see the true phase shift or horizontal shift. So the first thing that we do is we take our x or square root of x graph, and then we're going to flip it horizontally so that it flips back to the left, and then we're also going to then shift it to the right 3 units. So that's going to land about here, and then we are swooping off to the left. Our intercepts are going to be at 3, 0. Here, x value is 3, z value is 0, and then at 0, rad 3, and rad 3 is just a little bit shy of 2. So let's go ahead, and here is our graph in the xz plane, and we're going to use this to help us graph this function now in 3 dimensions. So if we graph it in 3 dimensions, in R3, what we notice here is that we're missing the y variable. And when we're missing a certain variable, that means that the graph is going to extend in the direction of the variable that is missing, or that variable, the y variable, gets to roam free. So the way that we approach this graph in R3 is, since we are missing one of the variables, we're going to graph this function in the plane of the 2 variables that it contains. So we graph it in the xz plane, and then after we do that, we will extend that graph in the direction of y. So we just graphed it in the xz plane up here, so we're going to try to create this image in the xz plane in 3-dimensional space. So the xz plane is this vertical kind of wall over on this side, and we saw, sometimes I find it to be easier to go ahead and use these ordered pairs here and convert them to ordered triples in R3. So the x coordinate was 3, the z coordinate was 0, and if we're in the xz plane, we're going to have x coordinate 3, z coordinate 0, but we're also going to have y is equal to 0 here. Again, an ordered triple is going to be x, y, and z. So we have 3, 0, 0 as an ordered triple that is on this surface. And then as well, we have 0, rad 3, which was just shy of 2. And again, since we're in the xz plane, the y coordinate is 0. So this is going to be 0 in the direction of x, 0 in the direction of y, and rad 3 in the direction of z. Again, we are just recreating these ordered pairs that we graphed in the xz plane here on the xz plane in 3-dimensional space. So here is that half of a parabola graph in the xz plane that we just graphed a few moments ago in 2 dimensions. Now that we have this, we simply need to extend it in the direction of y. So we'll extend this point in the direction of y. So basically they all just kind of come sideways like this in the direction of y, in the direction of the variable that's missing. And then let's kind of duplicate this that we are actually going to go ahead and define to be a trace curve. A trace curve, and let's pause here for just a quick minute to get our definition. A trace curve is a curve of intersection between a surface and a plane that is parallel to one of the coordinate planes. Now, the coordinate planes are the xy plane, the yz plane, and the xz plane. So let's see how and where we have trace curves when we're graphing the surface. So this curve here is considered to be a trace curve because it's going to be intersecting our surface, but also it's going to be contained within a plane that is parallel to the xz plane. So because it exists entirely inside a plane and it intersects our surface, this is called a trace curve. So we can use these trace curves to help us get the overall shape of our surface. So again, extending this point to the left and then drawing another trace curve, again, that exists entirely in a plane, the plane that is essentially, it looks like probably around y is equal to -3 or something like that. But so now we've got 3 trace curves here, and we're going to extend this one in the direction of y to kind of turn this more into a surface. Let's go ahead and solidify these dotted lines here so that we can see that we're actually looking at a surface here that swoops off like this. And we were able to use the trace curves, essentially taking the one curve in the xz plane and duplicating that in 3 other planes that are parallel to the xz plane, and then just kind of filling in to see what that surface must look like. So now let's pop over here to GeoGebra to check our answer. Notice I'm in the 3D calculator and I basically just typed in the surface, and this is 3-dimensional space, but I wanted to let's see, focus in here on our first octet. This is where we have our positive x-axis, our positive y-axis, and our positive z-axis. And as you can see, we do have that same curve where if we were to look at the xz plane, we can see that trace curve. I'm trying to get it right on where I'm looking straight down that y-axis. So we're actually looking at a curve in the xz plane here. But notice in this situation we've got our positive x's coming off to the right, which is not what we traditionally look at. So I'm going to flip this thing around like this so that our positive x's are coming off to the left, which looks a little bit more like what we started off with. And you can see that trace curve there that is in the xz plane, but we also, if we were to slice this thing with some planes that are parallel to the xz plane, we would see all of these are trace curves here. So we do have the correct surface. We do see that we have the same surface that we graphed. Now when we graphed it in R3, it looked a little bit more like this because the positive x-axis was coming out at us. But essentially, yeah, this GeoGebra 3D graphing software gives us a way of checking our surfaces, checking our answers to make sure that they're correct.